So in mathematics, a Cayley graph or Cayley diagram or group diagram is a graph that encodes the abstract structure of a group and is coined after its inventor, Arthur Cayley. Suppose that G is a group. Let's say it's a finite group and S is a generating set for G. That means that any element of the group G can be written as some combinations of element of S. Then the Cayley graph, which we denote by gamma, is a colored directed graph which can be constructed as follows. Each element G in the group is assigned a vertex. Vertex set is identified with the group G. Each generator S is assigned a color which will denote by C sub S. So the color here is a function on the generating set. And then any element G in the group and any element S in the set generating the group, the vertices corresponding to the elements G and GS are joined by a directed edge of the color corresponding to S, which is an element of the generating set. Okay. All right. So I would like to give some credit to the following site, which I use to illustrate the graph that I will show you in this lecture. Let us consider the cyclic group G, which is generated. So G here is a group which is generated by some element A, and we'll assume that A has order 3. That being said, then G will have, of course, the identity element. It will have A, it will have A product A, and then if you take A product A, that's A power 3, which will be the identity since A has order 3, right? So that's pretty much all you have. So this group here has 3 elements because it's generated by an element of order 3. Now let's look at the generating set here, a generating set here, S, is the singleton containing A. Okay, and like we said, we'll have a graph, and then in our graph, each vertex corresponds to an element in the group. So this is the identity element. Here we have an element of the generating set, and then you have A times A, which we denote by A squared. Now notice that so because our generating set only contains one element, so we'll only have one color. Okay, and we use this reddish color. We'll use this reddish color to denote our one color. So if I multiply E by A, I'm gonna get A. So the vertices E and A are joined by this edge, which is red, right? And now if I take A times A, that'll be A squared again. So the verteces corresponding to A and A squared are joined by this directed graph. And if I take A squared times A, I will get A cube, which is E. So these two are connected. These two vertices are connected by again a red edge. All right, let's consider another group. Let S3 be the set of all bijections on a set of 3 elements. 1, 2, 3. S3 is generated by two elements with two non-commuting elements R and F. And R send 1 to 2, 2 to 3, 3 to 1. F will send 1 to 1, 2 to 3, 3 to 2. So essentially F fixes 1 and swap 2 and 3. Okay, so we have 6 elements here. Let me identify them. We have E, we have F, we have RF, FR. They're distinct because they don't commute. We have R, and then we have R square. Now let's see what happened with our group contains 6 elements: E, R, R square, F, RF, FR, and our generating set S, we said, contains 2 elements, R and F. So I will use red, the red color for R, and I will use the green color for F. So R times E, right, will be R. So this, we get that. If you take R times R, get this. If we take R times R square, we get the identity. So we return right here. Now to generate F, I will need a green color, right? Because green corresponds to F. So we'll have this. But then to generate RF, I need a red color. So, but notice that if I take FR, if we take FR, this will actually correspond to, so how do we get, so we'll need to multiply F by R. So we'll take this red here, and then we'll multiply by this to get. And if we have F R times R, that'll be FR square, which corresponds to RF. Okay, and if we take RF times R, this will give us, just to make some space here, let me erase some things. So if I consider RF times R, this will be R square F, but R square is R cube F, but R cube is E, so we get EF, which is F. So when we multiply by this, we get F. Now, to join these two nodes, I'll multiply, let's see here. So we take F and we multiply it. If we take FR and we multiply by F, what we'll get is FR square, but FF is E, so that'll be R square. So we get this here. And if I have FR, if I take FR and multiply by F, we get FF let's see here. So if you have FR times F, I'm sorry, I got this wrong. So if we have RF times F, that'll be RF square, which is RE, which is just R. So we get this. So this is the Cayley diagram for S3. Let's look at the following group. This group is a non-cyclic group. G is we take the product. A is the group generated by A consists of EA and then A square, and then we take the Euclidean product of these two. This will consist of all other pairs of the type XY, such that X is in this set and Y is also in the same set. Okay, so we take all possible order pairs that we can get, that we can take from the sets, the group generated by A. You can see that this set will have 1, 2, 3, 4, 5, 6, 7, 8, 9 elements here. And our generating set S is taken from the order pair AE and EA. Okay, and we will use for AE, we will use the color red, and for EA we will use the color green. Now if we take this set here, it has 9 many elements. We have EA. First of all, we have EE, AE, A square E, EA, AA, A square A, EA square, AA square, and A square A square. All right, so that being said, if we start with the identity and then we multiply by AE, of course we're going to get AE. If we take AE and we multiply by itself, so we multiply component wise, so that will be A square, E times E is E. So we get this element here. Now if we take A square E and we multiply that by AE, we'll get A cube E, but A cube E is EE. So we're back here. Okay, and a similar calculations show these two diagrams here. And so on, right? Okay, now to get to EA, we can't use a red color. We'll need a green color. So to this end, we'll start with EE, and we multiply EE by EA, and we get this element here. And if we take EA times EA, we'll get EA square, which will be this element here. And now, if we take EA square times EA, we get EA cube, but A cube is E. So we are back here. Again, similar calculations show this arrow. For the last one, if you take A square E times EA, we're going to get A square A. So we are here. If we multiply A square A times EA, we'll get A square A square. If we take A square times EA, we're going to get A square E. So we're back here. And this shows the Cayley diagram of